Okay, so now we're going to talk about different tools for model selection, and in particular, what we're going to talk about now is learning curves. So as you may realize, it's suddenly quite dark in this room, and I don't know how to turn on the light. Really, that's just life. But now I explain why it's suddenly so weird and dark in the video. But okay, so what we're going to ask now is basically, what does a balanced model look like? What does a model look like when it balances bias and variance? Whoops. Okay, so first consider a case where we have a model with high bias. We basically have underfitting. So what we get then is that the accuracy of our model, both when we evaluate it on the training data and on the validation data or test data, is basically below our desired level of accuracy. So our model just doesn't perform very well, and there isn't really any change in the performance of our model when we increase the amount of training samples, or we increase the size of our training data. So what does a model with high variance then look like? So it basically looks like the following. So there is a huge gap between the performance of our model when we evaluate our training data and our validation data. So we have a very good performance in our training data, but we have a quite bad performance in our validation data, and they're only slowly converging towards each other when we're increasing the training samples. Then finally, when we have a perfectly balanced model, or when we have a model that has a nice balance between the bias and variance, it looks like the following. So to begin with, there is a quite big gap between the performance of the training data and the validation or the test data, but they are converging towards each other in a nice way here. So what you can basically think of here is that when you are in a case where the performance on the training data and the validation data looks like the following, you probably want to use a more complicated model somehow. So you are subject to underfitting, so you may want to sort of use a more complex model. In this case, however, you either want to reduce the complexity of a model, or if you think that the complexity that you're using for some reason is essential, you may want to see if you can increase your data set, so collect more data really. And what you have here is again a nice model. It's a good situation that you're in down here. Okay, so what you just saw was learning curves in theory. So we saw how the performance of a model on a training data set and on our validation data set can vary for different training sample sizes. We saw that in theory. You may ask, is this also something that we can do in practice? Is this something that we can do in Python? Fortunately, it is, and otherwise we would not have included this in the notebook. So what we're going to do to show this in practice is that we're going to import a learning curve from model selection in scikit-learn. And then what we get here is basically that we're using the pipe lasso from one of the previous videos. That's our pipeline for the lasso model. Then we're specifying that we're using the development data set. And then here we're specifying that we want to train a model at different sample sizes. And here we specify basically an array with the different sample sizes that we want to try out. And in order to score the different models that we get out of training a given type of model on different sample sizes, we use the negative mean square error, and then we're using tenfold cross-validation. Okay, so what we get out is then, or what we're going to use is that we're going to create this MSE underscore this pandas data frame. We're creating with the pandas data frame class constructor, and we are creating a column called train, which stores the negative of the mean across these 10 folds here when we evaluate the performance on our training data set. and also when we evaluate the performance in our test data set. And we're using the negative here because our scoring metric up here was also the negative mean square error. So we're back in a situation here where a good model has a low estimate here. And then we set our index to be the sample sizes that were associated with these different scores. And what we get out is the following here. So I'm just printing the 5 first rows here. But you can see here the sample sizes, they are the indices. And then we have the performance in our training data set and our test data set. Okay. And what you should notice here is obviously that when you have a low training data set for training, then the performance on training data set is super good, as we would expect, and the performance on our test data set is very bad. And we can see some kind of convergence here. And that is also what we see in the following graph here. So here, basically, I'm plotting the performance on the training data set and our test data set against each other. So what we have here is the size of the training data set, and this reflects the mean square error on the training data set associated with these different rounds of training, basically, and this reflects the performance on our test data set, what we use as test data set. Okay, so what you should notice here is that we have a log scale here, right? So the distance between these two is quite big here. So what you should notice here is, as I mentioned before, that when we have a small training data set, then the model that we obtain does not generalize very well. So we have a small error on our training data, but this huge gap here up to the performance on the test data. But when we increase the training data, and in particular when we get to around 220 observations or more, we see that there's quite good generalization. These are quite close to each other, which indicates that we have a balanced model. So if you compare this to this figure here, they actually look quite a bit like each other. So that's quite nice. It seems that we have a fairly well balanced model. Okay, so what I'm doing here is basically the same here. Here I'm just plotting basically the full range of performances when we had the different training data sizes. As you remember, we used tenfold cross-validation, which meant that we got a range of different measures of the performance for each different size of our training data set. So that's basically just what we're plotting here. We're plotting the range on the test data and on training data. We get a similar picture as before.